Hi guys, welcome back. So for our first lesson of semester 2, we are looking at simplifying radicals. For our essential question, we want to answer what is the goal when simplifying radicals. So make sure you elaborate on what our ultimate goal is when we are simplifying radicals. So for vocab, just a couple of terms. The first term is perfect square factors. Perfect square factors are just factors of a number that are perfect squares. So for example, the number 45, factors of 45 could be 9 times 5, and 9 would be your perfect square factor because the square root of 9 is 3. So remember earlier in the semester, in first semester, we talked about perfect square numbers, and our perfect squares were 1, 4, 9, 16, 25, etc. And so when we're looking at factors of a number, we're looking to see are any of these numbers factors of any given number, and that would be our perfect square factor. The next term is parts of a radical. And so I just want to kind of break it down and look at different parts of a radical before we move forward. And so if we had a radical, which we usually refer to as a square root, we have the number inside of the radical, which is referred to as the radicand. And we have the root or index of the radical. Now, the thing about a square root is that the root or index is an implied 2. So whenever you don't see a number written out in front of the radical, we know that this number here is an invisible 2. But you could also see a cube root, which would look like this, or a fourth root, which would look like this, etc., etc. So when we're looking for the square root of a number, we're looking for a number to the second power that equals that value. So for example, if we look for the square root of 25, we know that the square root of 25 is 5 because 5 to the second power is equal to 25. And so again, that invisible root implies that we're looking for that 2 value. Well, if we were looking for the cube root, let's say the cube root of 8 would be 2 because 2 to the third power, so again, that index or that root, 2 to the third power is equal to 8. So again, the number inside the radical is what I will refer to as a radicand, and the number on the outside of the radical is the root or index. All right, so before we get into our guided practice problems, there are a couple of problems I just want to kind of look at, just to kind of give us context as to what we're looking for when we're simplifying our radicals. So if we had the square root of 45, and this is the number that I just used in my example on the previous slide. If we're looking for the square root of 45, well, 45 is not a perfect square number. So if you were to type 45 into your calculator, you're going to get this big long decimal because 45 is not a rational number. So it's a decimal that goes on forever and ever and ever. So whenever you don't have a perfect square, we can still try to simplify our radical by removing the perfect square factors. And in some cases, the perfect square factor might be really obvious or really easy to find, but in other cases, it might not be. And the thing we have to make sure that we do is that we have to make sure that we remove the largest perfect square factor, just kind of like the greatest common factor that we learned when we talked about when we were factoring. We want to make sure that when we're simplifying our radical that we're removing the greatest perfect square number. And so I'm going to show you a method to help us find that, but I just want to kind of break it down so you guys understand what it is we're looking for. So we know that 45 is equal to 9 times 5. And we know that 9 is a perfect square. So if we were to break this apart within the radical, we can see that 9 times 5 gives us 45. Well, using the rules of radicals, we can go ahead and we can break this apart. And we can say that this is the same thing as the square root of 9 times the square root of 5. And then again, we know that 9 is a perfect square number. So then we can go ahead and we can simplify this radical, and the square root of 9 would give us 3. So in the end, this would simplify down to 3 square root 5, or 3 rad 5 is how I will read it, 3 radical 5. Now, again, if you were to type this number into your calculator, you're going to get this big long decimal. Well, if you were to do 3 times the square root of 5, you're going to get that same decimal because these are equivalent radicals. And so what we've done here is we've just simplified this by removing that perfect square number out of the radical. We take the square root of 9, and then 3 is no longer inside the radical because we've applied that square root to it. So let's look at another one. If we had the square root of 112. Again, sometimes it's going to be really easy to find, and other times it might not be so obvious what we're looking for. Well, 112 is the same thing as 16 times 7. Now we know that 7 is not a perfect square number. 7 is actually a prime number, so there's nothing that we can do to simplify that. But we do know that 16 is a perfect square number. So if we break this down within the radical, we can then separate our radicals, the square root of 16 times the square root of 7. And now we can go ahead and apply that square root to the 16. We know that the square root of 16 is 4. So then this would simplify down to 4 rad 7. 4 times the square root of 7, or 4 radical 7, 4 square root 7, however you want to read that. And so when we are simplifying our radicals, again, we're looking for those perfect square factors that we're able to divide out. Well, there, again, is not always obvious what that number is. And so what we're able to do to help us find that value is use the cake method that we used in first semester to help us break down these radicals. So that's what we're going to take a look at in our lesson today. So here we have the square root of 24. And we want to simplify the radical. And so what I'm going to do is I'm going to take the number, I'm going to take the radicand, so 24, and I'm going to put it inside of our cake box. So I'm going to take 24 and I'm going to put it inside our cake box. And remember, when we're caking our number, we're looking to divide out the smallest prime number as many times as possible, and then move on to the next smallest prime number. So let's just go ahead and list our prime numbers: 2, 3, 5, 7, 11, etc. And so we're going to divide out first 2 as many times as possible, and then we'll move on to 3, and then the others if necessary. So 24 divided by 2 gives us 12. We can divide out another 2. 12 divided by 2 gives us 6. We can then divide out another 2. 6 divided by 2 gives us 3. We can then not divide out another 2. We can then move on to the next smallest prime number, which is 3. And 3 divided by 3 is 1. And remember, our goal when caking is to get all the way down to 1 by dividing out. And so all of these numbers here on the left-hand side should be prime numbers. Now, when we are simplifying our radical, we're looking to find the number of, we're looking for groups of the index. And remember, with a square root, there's an invisible 2 there. So we're looking for groups of these prime numbers of 2. So we can see here that we have a group of 2 2s. And because it's a 2, we're looking for pairs. So 2 of each type of number. So you can see here that we have 3 2s actually, but because it's a square root, the 2s here, the pair of 2s is what gives us our perfect square factor. And so these numbers here are what I actually refer to as leftovers. And so what happens is the pairs are what give us our perfect square number. So if we were to multiply this back out, 2 times 2 would give us 4, and 4 would be the largest perfect square factor of 24. And so if I were to break this down the way that I did on the previous slide, then 2 times 2 would be 4. And then our leftovers would be 2 times 3, which would give us 6. And so again, when we put this back together, we divided each of these prime numbers out. So when we put them back together, we want to make sure that we multiply. So the square root of 4 would actually be 2, and then the radical 6 is what our leftovers are. And so I like to say that our leftovers go back inside the radical, just like leftovers go inside the refrigerator. So that radical kind of acts as our refrigerator. And so we simplify this and it becomes 2 radical 6. So again, the pairs are what give us that perfect square number. We then take the square root of that number, and that's what goes outside the radical. That's where we're able to pull outside of that radical. And then the numbers that I circle here are the numbers that do not have pairs. Those are our leftovers, and I multiply those and put those back inside the radical. So you'll see here that the number that we had the pair of actually is the single number that goes out in front of the radical. And if you had multiple pairs, then you would multiply those numbers together to put them outside of the radical. And we're going to see that in our example today as well. Okay. All right, so here we have 6 times the square root of 108. Now we're going to ignore that 6 until the very end. So right now we're just simply looking to simplify what's inside of this radical here. So in our cake box is just going to be our radicand, which is 108. And that's what we're going to cake first. So again, dividing out the smallest prime number as many times as possible. I'm going to start with 2 because 108 is an even number. So I can divide out that 2. 108 divided by 2 gives us 54. Divide by 2 again, because 4 is even, and that gives us 27. We cannot divide that by 2, though, because 7 is not even. Remember, to determine if a number is divisible by 3, we add up our digits, and I know that 27 is divisible by 3, but 2 plus 7 is 9, and 9 is divisible by 3. Therefore, 27 will be. So 27 divided by 3 gives us 9. Divide by 3 again. 9 divided by 3 is 3. And divide by 3 again, and we get to 1. So again, our index here is that invisible 2. So we're looking for pairs of numbers. So we have a pair of 2s, so that's going to contribute to our perfect square factor. We also have a pair of 3s, so that will also contribute to our perfect square factor. And then we have a leftover 3. So if I were to multiply all of these numbers out, that's going to give us 36. So 36 is actually the perfect square number that we're able to pull out of 108. And then our leftover is a 3. So we know that the square root of 36 is 6, and square root 3 is our leftover. So the square root of 108 simplifies to 6 radical 3. Now, again, remember that when we look at these boxes, those numbers are the numbers that actually give us the number on the outside. So if we just multiply 2 times 3, that's what's going to give us that outside number. So if you are comfortable with it, you don't have to write this out every single time. We can simply look and say, okay, we have a 2 and we have a 3, and that's going to be on the outside of our radical, so we can multiply those together. Now for this particular problem, we also had this 6 that was present to begin with. So once we've simplified our radical, we'll then put that 6 out in front in addition to what we have outside. So we will then multiply 6 times 6, radical 3, and we just multiply the outside numbers together. So 6 times 6 gives us 36, radical 3. And that is the simplified version of 6 times the square root of 108. All right, our last GP for today, the square root of 320. So what we're going to do is we're going to take our radicand, 320, and put that in our cake box. And start with our smallest prime number, divide that out as many times as possible. So we're going to start with 2 because 0 is an even number. So 320 divided by 2 gives us 160. Another even number, divide by 2 again. 160 divided by 2 is 80. Divide by 2 again. It gives us 40. Divide by 2 again. That gives us 20. Divide by 2 again, that gives us 10. Divide by 2 again, that gives us 5. 5 is not divisible by 2. 5 is not divisible by 3, but 5 is divisible by 5, and that gets us down to 1. So again, our index is that invisible 2. We're looking to pair up our numbers, put them in groups of 2. So we have a pair of 2s, we have another pair of 2s, we have a third pair of 2s, and we have a leftover 5. So what we're going to do is we have our leftover 5 that goes back inside the radical. And then if you want to multiply these out, you remember you can do that, or remember what we would do is we would just use one of each of these, and that's the number that goes outside. So we would have 3 2s that we have to multiply together on the outside. 2 times 2 is 4, and 4 times 2 is 8. So this simplifies down to 8 radical 5. And that is what that would simplify down to. If you were to multiply out all of these 2's, that would give you 64, which would be inside the radical, but then when you take the square root, that would give us 8. And that is simplifying radicals. Make sure that you have toolbox items for this GP, and if you have additional questions, please make sure that you note them in the margin so that you can ask me during our next Zoom meeting. And also don't forget to answer the essential question. I will see you at our next meeting.